There's something about stars that makes us think we know them. We see them every clear night, scattered across the dark, tiny points of light that seem perfectly still and permanent. They are so far away that their light takes years, sometimes centuries, to reach us, crossing distances our minds can barely hold. And yet we look up at them as if they were familiar, as if we understood them. But here is something you have been seeing all along without quite understanding. Stars do not shine steadily. They twinkle. They shimmer. They seem to breathe. That dancing light, that gentle flicker you noticed as a child lying on grass looking up, is not coming from the stars themselves. It's happening here, in the last 100 miles before the starlight reaches your eyes. It's our atmosphere, speaking in a language of light. The light that left a distant star perfect and unchanged, travelling for decades or centuries through the absolute stillness of space, trembles only when it enters our air. The twinkling is the atmosphere making itself visible, revealing currents we cannot feel, temperature changes too subtle to detect with our skin, an ocean of air in constant motion overhead. Tonight, we're going to follow a single photon on its journey from a distant star to your eye and discover what makes it dance in those final moments. Hello, and welcome to the Sleepy Astronomer. If you are joining me for the first time, welcome to this gentle exploration of the cosmos and the quiet wonders hidden in plain sight. And if you wandered with me through ancient galaxies or distant worlds, it's wonderful to have you back. Tonight, we turn our attention closer to home, to the invisible ocean that wraps around our planet and makes distant starlight shimmer. Whether you are settling into bed after a long day, or perhaps resting somewhere quiet while you imagine lying on grass beneath a field of stars, I'm so glad you're here. If you enjoy these peaceful journeys through cosmic wonders, don't forget to subscribe so you don't miss the next journey into the cosmos. And if this story calls to you, how starlight trembles and what the air reveals, a gentle rating and a share helps others find their way to these calm corners of the universe. Here is something you might not have considered. Every time you see a star twinkle, you are watching something invisible become visible. The atmosphere is always there, always moving. Wind carrying warmth and cold in layers and currents miles overhead. But we cannot see it. We cannot feel it from the ground. Starlight makes it visible. Each shimmer, each colour that flashes across a low star on the horizon, each gentle dance of light is the air announcing itself. The twinkling is not in the stars. It's in us. Or rather, in the ocean we swim through without noticing. So, take a deep breath, let your shoulders drop, and find your most comfortable position. The stars have been twinkling for as long as Earth has had an atmosphere to make them dance, and they will continue long after we are gone. But tonight, for a little while, we get to understand what we are seeing. Imagine a star, not our sun, but another one, perhaps 100 light years away, perhaps 200. The exact distance does not matter for our purposes. What matters is that it is far enough that its light, travelling at the fastest speed anything can travel, will take longer than a human lifetime to reach Earth. Deep in the core of this star, hydrogen atoms are being crushed together by unimaginable pressure, fusing into helium and releasing energy in the process. This is what stars do. This is all they do, really. They take the simplest element in the universe and squeeze it until it becomes something else, and that transformation produces light. Among the countless photons born in this stellar furnace, one photon, our photon, begins its journey outward. It does not have an easy time of it at first. The outer layers of a star are dense, filled with atoms that absorb and re-emit light, scattering it in random directions. A photon that forms in the core of a star like our Sun might take tens of thousands of years just to work its way to the surface, bouncing from atom to atom like a pinball in slow motion, travelling mere centimetres before being absorbed and re-emitted again and again and again. But eventually, and the word eventually is doing considerable work here, our photon reaches the star's surface. It breaks free, and suddenly, after all that struggling through stellar material, it finds itself in space. Empty space. Here is what space is, or rather, what it is not. It is not air. It is not dust, not in any meaningful sense. It is not anything, really. A vacuum so complete that if you could hold a cubic meter of interstellar space in your hands, you would find perhaps one hydrogen atom floating in it. Maybe two, if you are unlucky. In this emptiness, our photon travels in a perfectly straight line. Nothing deflects it. Nothing slows it. It moves at exactly 299,792,458 meters per second, a number that has been measured so precisely we have defined the meter itself in terms of how far light travels in a given time, rather than the other way around. Light does not speed up or slow down in a vacuum. It simply moves at the only speed it knows. This constancy is worth pausing over. The photon that left our distant star perhaps a century ago, perhaps when your great-grandparents were young, or before your country existed as a political entity, or during some war whose specifics are now studied by historians rather than remembered by anyone living, has been travelling, unchanged, all this time. It has crossed distances that make Earth's oceans look like puddles. If you could travel from London to New York in the time it takes light to cross a single light year, you would arrive before you had time to order a cup of tea. The photon has been travelling for 100 of these incomprehensibly vast distances, and it has not varied its course by even a fraction of a degree. There is something quietly beautiful about this. The universe is vast and chaotic. Stars explode, galaxies collide, black holes devour entire solar systems. But through all of it, a single photon can travel in a straight line, undisturbed, carrying the exact energy and colour it was given at birth, until it meets something. And eventually, after all those years or centuries, it does. Our photon crosses the outer reaches of the solar system. It passes through regions where spacecraft have ventured. The Voyager probes are out here somewhere, though the odds of our photon actually hitting one are so vanishingly small that we need not worry about it. Space is incomprehensibly large, and even things we send into it are incomprehensibly small by comparison. It continues inward, past the orbits of Neptune and Uranus, though those planets themselves are nowhere nearby. They are off tracing their own slow circles around the Sun, and space is so empty that our photon could cross the solar system 1,000 times without ever encountering anything larger than a grain of dust. Past Jupiter's orbit, past Mars. The inner solar system is slightly busier. There are more asteroids here, more debris from the formation of the planets, but still, mostly, it is nothing. And then ahead a small blue-green sphere appears in the photon's path. Earth. The photon is not aware of this, of course. Photons do not have awareness, they simply exist and move. But if it did have awareness, it might notice that this particular planet looks different from most of the others. Earth is wrapped in something, a thin shell of gas held close by gravity, thick enough to blur the surface beneath. An atmosphere. Most rocky planets do not have atmospheres, or if they do, the atmospheres are thin and insubstantial. Mars has an atmosphere you could barely call an atmosphere. Surface pressure roughly equivalent to standing 30 kilometers above sea level on Earth, which is to say, not much atmosphere at all. Venus has an atmosphere, certainly, but it is a crushing, poisonous thing that would be more accurately described as atmospheric punishment. Earth's atmosphere is different. It is thick enough to hold warmth, to carry water vapour, to support the kind of complex chemistry that leads to things like trees and fish and people looking up at stars. It is, by the standards of rocky planets, unusually substantial. And our photon, which has travelled for perhaps a century through perfect vacuum, is about to enter it. This is where things get interesting. The atmosphere does not have a sharp boundary. It is not as though there is vacuum on one side and air on the other, with a clear line between them. Instead, the atmosphere simply becomes gradually thicker as you descend toward Earth's surface. At the very top, 100 kilometers up, say, there are so few molecules that calling it air seems generous. It is more like occasional atoms that happen to be near Earth. Our photon enters this thin outer region, and for a while, nothing much changes. The few molecules it encounters are so sparse that they might as well not be there. It continues downward, though downward is somewhat misleading, as the photon is simply travelling in a straight line, and Earth happens to be in the way, passing through progressively denser layers of atmosphere. 60 kilometers up, 50, 40. The air is still thin by surface standards, but it is no longer nothing. There are enough molecules now that interactions become possible. Our photon is still travelling in a straight line, but that line is no longer quite as straight as it was in the vacuum of space. This is because of something called refraction, which we will discuss properly in the next chapter, but the essence of it is this: light slows down slightly when it moves through anything denser than vacuum, and when light slows down while travelling at an angle through a material, it bends. Not much. Not in a way that would be visible if you could somehow watch the photon's path, but enough that by the time it has passed through the full thickness of Earth's atmosphere, it will have been deflected from its original course by a measurable amount. 30 kilometers up, 20, 10. The air is now dense enough to be called air without irony. The photon has been bending and slowing, though slowing is relative. It is still moving at something very close to its vacuum speed, as it descends through layers of nitrogen and oxygen and water vapour, through temperature gradients and pressure changes, through an atmosphere that is, it turns out, not at all uniform. And this lack of uniformity is everything. Consider what our photon has been through. It was born in the core of a star, struggled for millennia to escape the star's outer layers, then travelled in perfect solitude for a century or more across the void. It has crossed distances so vast that human minds struggle to comprehend them. It has maintained its energy, its direction, its essential photonness through all of this. And now, in the last 100 miles, a distance you could drive in less than 2 hours if there were a road, something finally changes. The atmosphere our photon is passing through is not still. How could it be? The sun heats the Earth's surface unevenly. Oceans and forests and deserts and ice sheets all absorb and release heat at different rates. This creates temperature differences in the air above them. Warm air rises, cool air sinks, and the whole atmosphere churns in constant invisible motion. What this means is that the air our photon travels through is not uniform. It is layered, swirled, mixed. Pockets of warm air rising through cooler surroundings, streams of wind carrying parcels of air from one place to another, invisible turbulence that can be gentle or violent depending on conditions. And each pocket of air, each layer at a different temperature, bends light slightly differently. Warm air is less dense, the molecules are more energetic, more spread out. Cool air is denser, the molecules are packed more closely together. Light travels at slightly different speeds through these different densities, and when it crosses from one to another at an angle, it bends. So our photon descending through this churning ocean of air is bent, then bent again, then again. Each deflection is tiny, but they add up. By the time the photon reaches the lower atmosphere, the air you can actually breathe, it has been deflected from its original path by countless small perturbations. If the atmosphere were perfectly still and uniform, this would not matter. The photon would be bent once as it entered the atmosphere, then travel in a straight line to the ground. But the atmosphere is neither still nor uniform. It is moving, constantly, and so the path the photon takes through it changes from moment to moment. Which means that our photon, this ancient traveller, this carrier of starlight that has crossed a century of space unchanged, will arrive at your eye from a slightly different angle than the photon that arrived 1 second before it. The star has not moved, the light has not changed its essential nature, but the invisible ocean it must pass through in those final moments has shifted, and that shift becomes visible as a dance. You're lying on grass or standing in a field or perhaps sitting on a balcony late at night. You look up at a star. The star appears to shimmer, to shift position slightly, to change in brightness, not dramatically, not in a way that suggests the star itself is doing anything unusual, but just enough to notice. What you are seeing is not the star twinkling. The star is shining steadily, has been shining steadily for millions or billions of years, will continue shining steadily for millions or billions of years more. What you are seeing is the last 100 miles of the photon's journey, the part where it passes through air that cannot hold still. The twinkling is the atmosphere making itself visible. Every shimmer is a current of air you cannot feel. Every slight change in brightness is a pocket of warm or cool air drifting past overhead. The star is simply providing the light that reveals this motion, the way dust in a sunbeam reveals air currents in a room. This is worth appreciating. You cannot see the atmosphere directly. It is transparent, invisible. But starlight, travelling from incomprehensible distances, renders it visible in those final moments. The twinkling you have been watching since childhood is the air itself, speaking in a language of light. Our photon completes its journey. After a century of travel, after crossing distances that reduce Earth to a speck, after maintaining its course and energy through the vast emptiness of space, it enters your eye. It strikes a molecule in your retina, triggering a chemical reaction that sends a signal to your brain, and you see it. One photon among billions, all making the same journey, all trembling in that final passage through our ocean of air. Together, they create the gentle dance you call twinkling. The star itself has not moved. The light itself has not changed. Only the path through the air, invisible, ever-shifting, quietly turbulent, has varied. And that is enough to make the stars seem to breathe. We talk about the atmosphere as if it were a thin shell, a delicate membrane wrapped around the planet. And in cosmic terms, that is accurate enough. The atmosphere is vanishingly thin compared to Earth's diameter, a wisp of gas clinging to a rock. But from our perspective, standing at the bottom of it, the atmosphere is not thin at all. It is an ocean of air, hundreds of kilometers deep, pressing down on us with a real, measurable weight. Right now, as you listen to this, there is a column of air above you stretching all the way to space, and that column weighs about the same as a small car sitting on your shoulders. You do not notice this because the air inside your body is pushing back with equal pressure, and because you have been carrying this weight since birth and your body considers it normal. But the weight is there. The pressure is real. And this ocean of air, invisible though it is, has structure and texture and currents just as real as anything in the ocean of water. When you breathe, you are pulling in molecules that have been everywhere. The nitrogen molecule entering your lungs right now might have once been part of a thunderstorm over the Pacific, might have swirled through a hurricane, might have drifted in the jet stream over the Arctic. The oxygen molecule beside it could have been exhaled by a tree in the Amazon, absorbed by plankton in the Indian Ocean, released again, carried by wind currents halfway around the world. The atmosphere is not static. It cannot be. And this motion, this constant invisible churning, is what makes stars twinkle. To understand why, we need to understand what the atmosphere actually is, what makes it move, and what happens to light when it passes through air that refuses to hold still. The atmosphere, chemically speaking, is mostly nitrogen and oxygen. About 78% nitrogen, 21% oxygen, and the remaining 1% is a mixture of argon, carbon dioxide, water vapor, and trace amounts of various other gases that are present in such small quantities that they barely deserve mention. This composition has been roughly stable for hundreds of millions of years, maintained by the balance between photosynthesis and respiration, volcanic outgassing, and chemical weathering, life and geology working together in ways that are still not entirely understood. But while the chemical composition is relatively uniform, a sample of air from sea level and a sample from the top of Mount Everest would contain roughly the same proportion of nitrogen and oxygen. The physical properties of that air change dramatically with altitude and temperature. Air, like any gas, responds to temperature and pressure in predictable ways. Warm air is less dense than cool air because heat makes molecules move faster, spread out, occupy more space. This is not a metaphor. At the molecular level, temperature is motion. The hotter something is, the more vigorously its molecules are vibrating and bouncing around. In warm air, molecules are energetic, widely spaced, flying past each other at high speed. In cool air, they are sluggish, packed more closely together, moving more slowly. This difference in density has consequences. Warm air, being less dense, is lighter. It weighs less per unit volume than cool air, and because it weighs less, it rises. Cool air, being denser, sinks. This is convection, and it is happening all around you, all the time, invisibly. The sun does not heat the Earth's surface uniformly. This is partly because the Earth is a sphere. Sunlight strikes the equator more directly than it strikes the poles, and partly because different surfaces absorb and release heat at different rates. Water heats slowly and cools slowly. Rock heats quickly and cools quickly. Vegetation is somewhere in between. Snow and ice reflect most sunlight without absorbing it at all. What this means is that on any given day, at any given moment, the Earth's surface is a patchwork of different temperatures. A forest might be cool and shaded, while an adjacent parking lot bakes in the sun. The ocean retains yesterday's warmth while the land has already cooled in the evening air. A snow-covered mountain reflects heat, while the valley below absorbs it. Each of these surfaces heats the air directly above it. The air over the hot parking lot warms and rises. The air over the cool forest remains relatively still. The air over the ocean picks up moisture and warmth and begins to drift. And because air is a fluid, it flows, it mixes, it cannot stay in neat separate layers. These pockets of warm and cool air begin to interact. Warm air rises, creating a region of lower pressure beneath it. Cool air flows in to fill the gap. This moving air is wind, and wind carries its own temperature and moisture with it, creating new patterns of heating and cooling wherever it goes. The whole atmosphere becomes a vast, three-dimensional mixing of air at different temperatures, different pressures, different levels of moisture content. And it never stops. The sun rises every morning and heats the surface anew. The Earth rotates, carrying different parts of the surface into and out of sunlight. Seasons change, shifting the patterns of heating. Weather systems form and dissipate. The atmosphere is in constant motion from the surface all the way up to the edge of space. This would be interesting enough on its own, but for our purposes, understanding why stars twinkle, what matters is what this motion does to light. Light, it turns out, is affected by the density of the material it travels through. When light moves from one material into another, from air into water, say, or from vacuum into air, its speed changes. In a vacuum, light travels at its maximum possible speed. In anything denser than vacuum, it slows down slightly. The denser the material, the more it slows. This slowing is not dramatic. Light in air travels at about 99.97% of its vacuum speed, which is to say, nearly the same. Light in water slows to about 75% of its vacuum speed. Light in diamond being particularly dense and having a particularly strong effect on light, slows to about 41% of its vacuum speed. The slowing itself would not be visible. If light simply slowed down while continuing in a straight line, we would never notice. But light does not continue in a straight line when it slows down. It bends. This bending is called refraction, and while the physics of it involves wavefronts and phase velocities and other concepts that require more mathematical precision than is comfortable for a conversation meant to help you fall asleep, the essence can be understood with a simple analogy. Imagine you are walking across a smooth, flat beach toward the ocean. You are walking at an angle to the water's edge, not straight toward it, but diagonally. Your left foot reaches the water first. It sinks into the wet sand, which provides more resistance than the dry sand you have been walking on. Your left foot slows down while your right foot is still on dry sand, still moving at your normal walking speed. What happens? You turn. Without meaning to, without thinking about it, your body pivots slightly to the left, because one foot is moving slower than the other. By the time both feet are in the water, you are walking in a slightly different direction than you were on the beach. Light does the same thing. When a beam of light strikes a denser material at an angle, one side of the beam enters first and slows down while the other side is still travelling at its original speed. The beam bends toward the denser material. This is refraction, and it happens any time light crosses a boundary between materials of different densities. You can see this yourself if you place a straight object, a pencil, a straw, anything rigid, partially into a glass of water. The object appears to bend at the water's surface. It does not actually bend, of course. What bends is the light reflecting off the submerged portion of the object. That light travels through water, crosses the boundary into air, bends as it makes the transition, and arrives at your eye from a different angle than you would expect. Your brain, interpreting this bent light, perceives the object as bent. This same principle, light bending when it crosses between materials of different densities, is responsible for mirages on hot roads, for the way objects appear distorted when viewed through the shimmering air above a candle flame, for the bending of sunlight as it passes through the Earth's atmosphere at sunset, making the sun appear slightly higher in the sky than it actually is. And it is responsible, ultimately, for twinkling stars. Now here is where it becomes relevant to stars. The atmosphere is not a single uniform material. It is a constantly shifting mixture of air at different temperatures and therefore different densities. A photon travelling down through the atmosphere does not cross one boundary from vacuum to air and bend once. It crosses countless boundaries between pockets of air at slightly different temperatures, and it bends very slightly at each one. If the atmosphere were perfectly still, if the air were arranged in neat, stable layers with warm air on top and cool air below, with no mixing, no wind, no turbulence, this would still cause refraction, but it would be consistent. Every photon from a given star would follow the same path through the atmosphere. The star would appear in a slightly different position than it actually is, shifted by the cumulative effect of all that bending, but it would appear steady and unmoving. The atmosphere, however, is not perfectly still. It is not arranged in neat layers. It is turbulent. Turbulence is a word we use to describe chaotic, swirling motion in fluids. You have experienced it if you have ever been in an airplane that hit rough air and started bouncing around. That is atmospheric turbulence. Pockets of air at different temperatures and velocities mixing in unpredictable ways, creating eddies and vortices and swirls that push the aircraft up and down and side to side. The same thing is happening all the time, at all altitudes, even on calm days when the ground-level air feels perfectly still. High above you, in the middle and upper atmosphere, air is flowing, mixing, creating turbulence that you cannot feel but that light can detect. The atmosphere can be thought of as a series of layers, though these layers are not as distinct as, say, the layers in a cake. There is the troposphere, where we live and where weather happens, extending from the surface up to about 10 or 12 kilometers. Above that is the stratosphere, where the ozone layer lives, extending up to about 50 kilometers. Higher still are the mesosphere and thermosphere, increasingly thin regions where the air is so sparse that it barely deserves the name. Turbulence occurs in all these layers, but it is strongest in the troposphere where temperature differences are most pronounced, and weather systems create large-scale mixing. The jet streams, rivers of fast-moving air high in the troposphere, are particularly turbulent, with wind speeds that can exceed 200 kilometers per hour and temperature boundaries sharp enough to create significant refraction. Even on a calm night when the surface air is perfectly still, the upper atmosphere can be churning with activity. Photons from a star, passing through these layers, encounter a constantly changing maze of temperature and density variations, each one bending the light by a tiny amount, the cumulative effect creating the shimmer you see from the ground. A pocket of warm air rises through cooler surroundings. It does not rise smoothly. As it rises, it interacts with the air around it, creating swirls and eddies along its edges. These eddies are regions where the temperature and density change rapidly over short distances. A photon passing through one of these regions gets bent more than a photon passing through calmer air. The scale of these eddies varies enormously. Some are large, hundreds of meters across, lasting for minutes or hours. Others are small, centimeters or even millimeters across, forming and dissipating in seconds. Starlight passing through the atmosphere encounters this entire range of turbulent scales, from massive weather systems down to tiny swirls, too small and brief to have names. What matters for twinkling is not the size of the turbulence, but its effect on light. Even small-scale turbulence can create measurable refraction if the temperature gradients are steep enough. A photon might pass through a region where the temperature changes by a few degrees over the span of a few meters. Not much by human standards, but enough to bend light slightly, enough to contribute to the overall shimmer. And because the turbulence is constantly shifting, warm pockets rise and cool, eddies form and dissipate, wind pushes air from one place to another. The pattern of bending changes from moment to moment. The path a photon takes through the atmosphere, this second is different from the path a photon takes the next second, even if both photons are coming from the same star. This is twinkling. The star is shining steadily. The photons are leaving the star at a constant rate, travelling in perfectly straight lines through the vacuum of space. but in the last 100 miles passing through our turbulent atmosphere, those perfectly straight paths get bent by different amounts depending on exactly which pockets of air the photons happen to pass through. The result is that the star's light appears to shimmer. The position of the star seems to shift slightly back and forth. The brightness fluctuates as turbulence sometimes focuses the light toward your eye and sometimes defocuses it. The star seems alive, breathing, dancing. But the star has not moved. The star is not breathing. What you are seeing is the atmosphere itself, revealed in the trembling of starlight. Think about what this means. Every time you look up at a twinkling star, you are watching invisible currents of air miles overhead. You are seeing temperature differences too subtle to measure with your skin, convection patterns that operate on scales too large to perceive directly, turbulence that exists in 3 dimensions through hundreds of kilometers of atmosphere. The atmosphere is performing an endless ballet of rising and sinking, warming and cooling, mixing and separating. Warm air from tropical regions drifts toward the poles. Cool air from polar regions sinks and spreads toward the equator. The rotation of the Earth deflects these flows, creating the trade winds, the westerlies, the polar easterlies, global patterns of circulation that have been flowing for as long as the Earth has had an atmosphere thick enough to support them. Within these global patterns are regional patterns, monsoons, sea breezes, mountain winds. Within the regional patterns are local patterns, thermals rising from sun-heated ground, downdrafts from cooling air, eddies forming where wind meets obstacles. And within these local patterns are smaller patterns still, down to scales of meters and centimeters, all of it nested within itself like Russian dolls made of moving air. Starlight passes through all of it. Every layer, every scale of motion, every temperature gradient contributes to the bending. The cumulative effect is what you see as twinkling, the integrated signature of atmospheric complexity rendered visible by light that has travelled further than minds can comfortably grasp. The atmosphere is transparent. We cannot see it under normal circumstances. But starlight, arriving from distances measured in light years, makes it visible in those final moments before reaching your eye. Each twinkle is a signature of motion, of mixing, of the constant, restless energy of air that cannot and will not hold still. There is an intimacy to this that deserves consideration. The atmosphere is not separate from you. You are inside it, breathing it, sustained by it every moment of your life. The oxygen molecules that keep your cells alive were mixed and distributed by the same atmospheric circulation that makes stars twinkle. The warmth that keeps you comfortable on a mild day is the result of the same solar heating that creates convection and turbulence overhead. When you watch a star twinkle, you are not observing something distant and separate. You are watching the atmosphere you live in reveal its nature, using starlight as a tool. The twinkling happens in your sky, in your air, in the space between your eyes and the edge of the atmosphere. It is yours in a way that the stars themselves can never be. The stars belong to the universe. They were here long before Earth existed and will be here long after it is gone. But the twinkling belongs to Earth, to this particular planet, with its particular atmosphere, its particular balance of temperature and pressure and turbulence that creates exactly this dance of light. This is why stars do not twinkle from space. Astronauts aboard the International Space Station, looking out at the same stars you see from Earth, report that the stars shine perfectly steadily. There is no atmosphere up there to bend the light, no turbulence to make it dance. The stars appear as they truly are, constant points of light against the black. Down here, though, we see them through our ocean of air, and that ocean, for all its transparency, for all that we move through it, without noticing, leaves its mark on everything we see. There is something rather lovely about this. We like to think of space as the great unknown, the final frontier, the place of mystery and wonder, and it is all those things. But the atmosphere, this thing we breathe, this invisible ocean we have lived in all our lives, turns out to have mysteries of its own. It is complex enough, dynamic enough, turbulent enough to make distant starlight dance. Every breath you take moves through this same air. Every time you feel wind on your face, you are feeling a tiny part of the vast circulation that encompasses the entire planet. And every time you see a star twinkle, you are watching that circulation reveal itself, written in light that has travelled for decades or centuries, just to tremble in its final passage through our sky. The ocean of air is always there, always moving, always mixing warm and cool in patterns that shift with the hour, with the season, with the weather. It is never the same twice, and because it is never the same twice, the stars never twinkle in quite the same way twice. Each shimmer is unique, a product of that particular moment's particular pattern of atmospheric turbulence. The twinkling you see tonight is different from the twinkling you saw last night, will be different from the twinkling you see tomorrow. The stars are constant, but the air between you and them is not, and so the dance continues, night after night, never quite repeating, never quite still. If you've spent any time looking at the night sky, and if you are listening to this you probably have, you may have noticed something curious. Not all the bright lights up there behave the same way. Some shimmer and dance, others shine with calm, steady light, as if immune to whatever atmospheric turbulence makes the stars perform their gentle ballet. This is not imagination. Some lights in the night sky genuinely do not twinkle, or at least they twinkle far less than stars do, and the reason for this is both simple and illuminating, in the literal sense, as it happens to involve the way light reaches your eyes. The distinction comes down to apparent size, or rather, to whether the object you are looking at appears as a point or as a disk. Stars, even the closest ones, are incomprehensibly far away. Alpha Centauri, the nearest star system to our Sun, is about 4 light-years distant. 4 years of travel at the speed of light. 40 trillion kilometres. That is far enough that even though the stars themselves are enormous, Alpha Centauri A is slightly larger than our Sun, they appear from Earth as dimensionless points of light. You cannot see a star as a disk, no matter how powerful your telescope. Even the Hubble Space Telescope, observing from above Earth's atmosphere with optics far superior to the human eye, cannot resolve stars into disks. They remain points, infinitely small in angular size, all their light concentrated into a single direction. When atmospheric turbulence bends the path of light from such a point source, it bends all of it together. Every photon from that star is travelling along essentially the same path through the atmosphere. If turbulence shifts that path slightly to the left, all the photons shift left. If it bends the path to the right a moment later, all the photons shift right. The star's position appears to jump around, and its brightness fluctuates as the atmosphere alternately focuses and defocuses the light. This is twinkling in its purest form, a point source of light being buffeted by atmospheric motion, its image dancing because there is no size to average over, no spread to smooth out the variations. Planets, however, are different. Planets are close, not close in any absolute sense. Venus at its nearest is still about 40 million kilometres away, which is far enough that light takes over 2 minutes to make the journey. But compared to stars, planets are practically neighbours. They orbit the same sun we do, sharing the same small region of space, and this proximity makes all the difference. Because they are close, planets appear as disks, not large disks. Venus at its brightest subtends an angle of about 1 arc-minute, which is to say 1/60th of a degree, which is to say very small. You cannot see this disk with the naked eye. Your eye is not quite good enough to resolve something that small, but the disk is there nonetheless, and more importantly, the atmosphere can resolve it. What this means is that light from a planet is not coming from a single point. It is coming from many points spread across the planet's disk. Light from the left edge of the planet travels through one patch of atmosphere. Light from the right edge travels through a slightly different patch. Light from the center travels through yet another patch. Atmospheric turbulence still affects each of these paths. The turbulence does not disappear just because you are looking at a planet instead of a star. But now, instead of all the light shifting together, different parts of the planet's light are shifted in different directions. Some photons are bent left, others right, others up or down or not at all, depending on which particular pocket of turbulent air they happen to pass through. The result is averaging. The shifts cancel each other out, at least partially. Your eye, or your telescope, receives light from all across the planet's disk simultaneously, and the various turbulence-induced shifts and shimmers average together into something much steadier than the wild dance of a point source. The planet still twinkles technically. If you were to measure its brightness with very precise instruments, you would detect fluctuations. But these fluctuations are much smaller than those of a star, small enough that to the naked eye the planet appears to shine calmly and steadily. This is why Venus, hanging bright in the evening or morning sky, does not shimmer the way stars do. It glows with steady golden light, a light bright enough to cast shadows if you know where to look, and that steadiness is a consequence of its apparent size. Even though Venus is just barely too small for your eye to resolve as a disk, it is large enough for the atmosphere to treat it as one, large enough for the averaging effect to smooth away most of the twinkling. Jupiter is steadier still. Jupiter is enormous, more than 11 times Earth's diameter, and while it is much farther from us than Venus ever gets, it is still close enough to appear as a respectable disk through even a small telescope. More disk means more averaging, and more averaging means less twinkling. Jupiter shines with a calm, cream-coloured light that barely fluctuates at all. Mars follows the same pattern. When Mars is close to Earth, which happens roughly every 2 years when our orbits bring us near each other, it appears relatively large and steady. When Mars is on the far side of the Sun from us, it appears smaller and twinkles more, though never as much as a true star. This gives you a way to distinguish planets from stars if you're ever uncertain which is which. Find a bright light in the sky, watch it for a while. If it twinkles, if its light seems to shimmer and dance, if its brightness fluctuates visibly, you are almost certainly looking at a star. If it shines steadily, calm and unwavering, you are probably looking at a planet. The word planet comes from the Greek planets, meaning wanderer, because planets move against the background of stars over the course of nights and weeks, while stars maintain their relative positions. But you do not need to watch for motion to identify a planet. The steadiness of its light is often enough. The moon, of course, does not twinkle at all. The moon is close enough and large enough that it clearly appears as a disk that subtends about half a degree of sky, large enough to be obviously circular even to the naked eye. Light from the moon comes from thousands of points spread across its visible face, and while atmospheric turbulence does affect this light, the averaging over such a large disk is so complete that twinkling becomes essentially undetectable. You can see atmospheric turbulence affecting the moon, but not as twinkling. Instead, it shows up as shimmering at the moon's edge when the moon is low on the horizon, or as slight distortions in the fine details of the lunar surface when viewed through a telescope. The same turbulence that makes stars dance simply blurs the moon a bit, softening edges that would otherwise be sharp. The Sun, being even larger and closer than the moon, is similarly immune to twinkling, though you should not, of course, be staring at the Sun to check this. The Sun's light, even when atmospheric turbulence is bending and distorting it, is far too intense for safe viewing without proper filters. But if you could observe the Sun safely during the brief moments of sunrise or sunset when its light is dimmed by atmosphere, you would see the same principle at work, a large disk, immune to the twinkling that affects point sources. There is something rather elegant about this size-dependent behaviour. The same atmospheric turbulence affects all light equally. It does not distinguish between photons from stars and photons from planets. But the consequences of that turbulence depend on the apparent size of the source. Point sources twinkle because they have no size to average over. Extended sources do not twinkle, or twinkle less, because they do. It is worth noting that this size threshold is not absolute. There is no sharp boundary where objects suddenly stop twinkling. Instead, there is a gradual transition. Very small extended sources, objects just barely larger than points. Twinkle almost as much as true points. Larger sources twinkle less. Very large sources barely twinkle at all. The transition is smooth, controlled by the ratio between the source's apparent size and the characteristic size of atmospheric turbulence. This characteristic size varies with conditions. On a night of strong turbulence, when the atmosphere is particularly active, with vigorous mixing and sharp temperature gradients, the turbulent cells are smaller, and even moderately extended sources might twinkle noticeably. On a night of weak turbulence, when the air is unusually stable and calm, only the smallest point sources show significant twinkling. Astronomers have a term for this: seeing. Good seeing means stable air with minimal turbulence, allowing telescopes to capture sharp images. Poor seeing means active turbulence that blurs and distorts everything. The distinction between stars that twinkle and planets that do not is essentially a manifestation of seeing conditions visible to the naked eye. On a night of excellent seeing, stars twinkle less than usual. Their light still shimmers, but gently, slowly, with fluctuations that are smaller and less frequent. On a night of terrible seeing, even planets might show slight fluctuations, though they will still be steadier than stars observed under the same conditions. Position in the sky matters too. Objects low on the horizon, whether stars or planets, pass through more atmosphere than objects overhead. More atmosphere means more opportunities for turbulence to affect the light, which means more twinkling for point sources, and potentially some twinkling even for extended sources. A planet near the horizon might shimmer slightly, while the same planet high in the sky shines perfectly steady. To understand why position matters so much, consider the geometry. When you look straight up at the zenith, the point directly overhead, your line of sight passes through the atmosphere more or less vertically. The path length through the air is at its minimum, perhaps 100 kilometers from the edge of space down to your eye. When you look at the horizon, your line of sight passes through the atmosphere at a shallow angle, like light skimming across the surface of water. The path length increases dramatically. Instead of 100 kilometers, you might be looking through 300, 400, even 500 kilometers of air, depending on exactly how low the object is. More air means more turbulence, more temperature variations, more opportunities for refraction to bend the light. It also means that the light passes through denser layers of atmosphere for longer. The air near the ground is thicker and more turbulent than the air higher up, and horizon-skimming light spends most of its journey in these lower, denser layers. This is why, if you watch Venus or Jupiter rising or setting, you might occasionally catch them twinkling more than usual. They are still averaging over their disks, but the amount of turbulent atmosphere they are looking through has increased so much that even averaging cannot completely smooth out the variations. Stars near the horizon, meanwhile, can twinkle spectacularly. Not only does their light shimmer in position and brightness, but it can also flash different colours, red, blue, green, white, as atmospheric turbulence separates the different wavelengths of starlight and sends them along slightly different paths. This chromatic twinkling is most pronounced for stars very low on the horizon, where the path through the atmosphere is longest and the turbulence most pronounced. Sirius, the brightest star in our night sky, is famous for this. In winter, when Sirius is visible from the northern hemisphere, it often appears low in the southern sky. Under these conditions, Sirius can flash with remarkable colours, a lighthouse star blinking red and blue and green in rapid succession as turbulence plays with its light. People who do not understand the cause of this chromatic twinkling sometimes report Sirius as a UFO, which is understandable if you're not expecting a star to behave that way. But Sirius is not doing anything unusual. It is simply a bright star positioned low enough that atmospheric turbulence can reveal the full spectrum hidden in its white light. The lesson in all of this is that apparent size matters. It is the difference between the wild dance of starlight and the calm glow of planets. It is why the moon and sun shine steadily while stars shimmer. It is why some nights are better for observing than others, and why astronomers go to such lengths to build telescopes on high mountains where the air is thin and stable. If you have ever wondered why major observatories are built in remote high-altitude locations, places like Mauna Kea in Hawaii, the Atacama Desert in Chile, or the Canary Islands, atmospheric stability is a large part of the answer. High altitude means less atmosphere above you, which means less turbulence to fight through. Dry climates mean less water vapour in the air, and water vapour creates its own turbulence as it condenses and evaporates. Remote locations far from cities also tend to have more stable air. Cities create heat islands, regions of warmer air rising from pavement and buildings, that generate additional turbulence for miles downwind. Mountains that rise above the local weather patterns can offer windows of remarkably calm air, nights when the seeing is so good that even stars barely twinkle and telescopes can capture details that would be impossible under normal conditions. Amateur astronomers learn to read the twinkling. On a night when stars are twinkling violently, they know that fine planetary details will be blurred and jumping around, making high magnification observation frustrating. On a night when stars twinkle gently or barely at all, they bring out their highest power eyepieces, knowing that the atmosphere will cooperate and reveal details that are usually hidden. When you look up at the night sky and see Venus shining calmly in the west, while a nearby star twinkles frantically, you are witnessing a demonstration of geometry and statistics. Venus is close enough to appear as a small disk. The star is far enough to appear as a point. Both are affected by the same atmospheric turbulence, but only the star shows it clearly, because all of its light arrives along a single path that turbulence can shift wholesale. It is in its own way rather wonderful. The twinkling of stars tells you something fundamental about distance. It marks the distinction between the solar system and everything beyond. Objects close enough to show a disk are part of our immediate cosmic neighbourhood. Objects that appear as twinkling points are citizens of the wider galaxy, so far away that even their enormous size cannot overcome the tyranny of distance. There is a kind of poetry in this. The planets are our siblings, orbiting the same star, sharing the same small corner of space. They shine steadily, calmly, as if their proximity to us grants them immunity from the atmosphere's restlessness. The stars, meanwhile, are strangers from vast distances, and the atmosphere treats them roughly, bouncing their light around, making them dance. You can think of it as the atmosphere sorting the sky for you. Steady lights are nearby, planets, the moon, the sun, objects that belong to our local family. Twinkling lights are distant, stars, galaxies, if they were bright enough to see, objects that exist in the realm beyond our solar system. This sorting is not perfect, of course. Artificial satellites can appear as steady lights if they are bright enough and high enough, though they move visibly across the sky in a way that planets do not. Aircraft appear as steady lights too, though usually with a giveaway of red and green navigation lights blinking in a regular pattern. And under unusual atmospheric conditions, even planets can twinkle slightly, while some stars might appear steadier than normal. But as a general rule, the distinction holds. Twinkle means distance. Steady means nearness, and all of it comes down to apparent size, to whether the object projects a single point of light or a small disk, and whether the atmosphere can average over that disk or must treat it as indivisible. Next time you are outside on a clear night, find a bright planet, Venus if it is visible, or Jupiter, or even Mars, if it is in a favourable part of its orbit. Watch it for a moment. Notice how calmly it shines, how steady its light is compared to the surrounding stars. Then find a star and watch it twinkle. Same atmosphere, same turbulence, same bending of light. But one object is close enough to appear as a disk, and the other is so far away that it remains forever a point. The steady light and the dancing light, both beautiful, both revealing something about the nature of distance and the behaviour of light passing through our restless ocean of air. If you watch the night sky with any regularity, you may have noticed that stars do not all twinkle in the same way. Some shimmer gently, with slow, smooth variations in brightness. Others flash rapidly, their light seeming to strobe as they dance. Some stars near the horizon put on remarkable displays of colour, cycling through reds and blues and greens in quick succession. Others maintain their colour even as their brightness fluctuates. These variations are not random. They follow patterns, and these patterns can tell you things about the atmosphere, about the star itself, and about the geometry of the observation. Learning to read twinkling is learning to read the sky. The most obvious pattern is this. Stars near the horizon twinkle more than stars overhead. This is not a subtle effect. A star hanging low in the sky can twinkle so dramatically that it seems almost to blink on and off. The same star, observed when it is high overhead, might twinkle so gently that you could almost mistake it for a planet. We have already touched on the reason for this, path length through the atmosphere. When you look at the horizon, you are looking through far more air than when you look straight up. More air means more turbulence, more temperature variations, more opportunities for refraction to bend the light in unpredictable ways. But there is more to it than simple path length. The air near the ground is fundamentally different from the air higher up. It is denser, for one thing. Atmospheric pressure decreases with altitude, and denser air means more pronounced refraction. It is also more turbulent. The ground absorbs heat during the day and releases it at night, creating temperature gradients and convection currents that churn the lower atmosphere into a complex, ever-changing mixture. When you look at a star near the horizon, its light spends most of its journey through the atmosphere in these lower, more turbulent layers. The path is not just longer, it is passing through the worst part of the atmosphere, the part where turbulence is strongest and most chaotic. The result can be spectacular. Stars very low on the horizon, within a few degrees of the horizon line, can appear to boil. Their light does not just shimmer, it seems to writhe and pulse, the star's position jumping around so much that it becomes difficult to focus on. If you watch through binoculars or a telescope, the effect is even more pronounced. The star's image can split temporarily into multiple images, dance apart and back together, change shape from a point to a streak and back again. This is atmospheric turbulence in its full chaotic glory, revealed by starlight that has the misfortune to pass through hundreds of kilometers of restless air. The colours that sometimes appear in twinkling stars are particularly worth examining. Not all twinkling involves colour changes. Most of the time, a star simply varies in brightness while maintaining its colour, but under the right conditions, particularly for bright stars low on the horizon, you can see colours flash across the star's light in rapid succession. This happens because different colours of light refract by different amounts. The physics of this involves the wavelength of light and how it interacts with the material it is passing through, but the upshot is straightforward. Blue light bends more sharply than red light when passing through a refracting medium like air. Under normal circumstances, this does not matter. All the colours that make up a star's white light travel together, bend together, arrive at your eye together. The star appears white, or perhaps slightly coloured depending on its temperature, but the colour is stable. But atmospheric turbulence can separate the colours. When a pocket of turbulent air bends the star's light, it bends the blue component more than the red component. If the turbulence is strong enough, the blue and red light can be sent along paths that differ by enough that your eye sees them at slightly different times or from slightly different apparent positions. For a moment, the star might appear blue as the blue light reaches your eye while the red light is bent away. A fraction of a second later, the turbulence shifts, and now the red light reaches you while the blue is deflected. The star appears to flash red, then blue again, then perhaps green as the blue and yellow components arrive together, while the red is missing. The sequence repeats, never quite the same twice, creating a chromatic display that can be mesmerizing to watch. Sirius is famous for this. It is the brightest star in the night sky, and during winter months in the northern hemisphere, it appears relatively low in the southern sky. Under these conditions, Sirius can put on a remarkable show of colours, reds and blues and greens flashing in quick succession, the star seeming to pulse with multicoloured light. People unfamiliar with the phenomenon have reported Sirius as a UFO, which is understandable if you are not expecting a star to behave that way. A bright light, flashing different colours rapidly certainly seems unusual, but Sirius is not doing anything strange. It is simply a very bright star positioned low enough that atmospheric turbulence can fully express itself in its light. This same effect, atmospheric dispersion, as it is formally called, is responsible for the green flash sometimes seen at sunset. When the sun is just at the horizon, its light passes through so much atmosphere that the different colours can be separated enough to be seen individually. The red light is bent less and appears to set first. The blue light is bent more strongly and is usually scattered away by the atmosphere. But the green light, being intermediate, can sometimes be seen for a brief moment as the last visible colour before the sun disappears. The green flash lasts only a second or two, requires clear atmospheric conditions to see, and is essentially a magnified version of the same colour separation that makes stars twinkle chromatically. The speed of twinkling also varies, and this too follows patterns. On some nights, stars twinkle slowly, their brightness changing over several seconds. On other nights, the twinkling is rapid, with fluctuations happening many times per second. The difference comes down to the scale and speed of atmospheric turbulence. Large-scale turbulence, massive pockets of air rising or sinking over timescales of minutes, creates slow variations. The star's light passes through these large structures, and as the structures slowly shift and evolve, the refraction changes slowly too. The star brightens gradually, dims gradually, the whole cycle taking several seconds or more. Small-scale turbulence, tiny eddies and vortices forming and dissipating in fractions of a second, creates rapid variations. The star's light is being bent by structures that change faster than your eye can follow, and the result is twinkling that looks almost like flickering, the star's brightness changing many times per second in a rhythm too fast to count. Most nights feature a mixture of both. There are large-scale currents and small-scale eddies happening simultaneously at different altitudes, and the star's twinkling reflects this complexity. You might see a slow variation in overall brightness with rapid flickers superimposed on top, a star that dims gradually over several seconds while flickering rapidly the whole time. Weather patterns influence twinkling in predictable ways. On a calm, stable night, perhaps after a high-pressure system has been sitting over your location for days, with clear skies and gentle winds, the atmosphere tends towards stability. Large-scale mixing is minimal. Turbulence is weak. Stars twinkle gently if at all, and the twinkling tends to be slow and smooth. On a night with active weather, perhaps before or after a storm, when air masses are mixing and the atmosphere is energetically rearranging itself, turbulence is strong and chaotic. Stars twinkle dramatically, with rapid fluctuations and frequent color changes for bright stars near the horizon. The sky might be clear enough to see stars, but the atmosphere above is churning with enough vigor to make steady observation difficult. Wind aloft matters particularly. Even on a calm night at ground level, there can be strong winds in the upper atmosphere, the jet stream and other high-altitude currents that move air rapidly across continents. These winds create shear, regions where air at different altitudes is moving at different speeds, and shear creates turbulence. A night with strong jet stream activity can have poor seeing even if the surface conditions are perfectly calm. Astronomers have learned to check upper atmospheric wind forecasts before planning observations. A night with gentle winds aloft will likely have good seeing, allowing telescopes to capture sharp images of planets and fine details in deep sky objects. A night with jet streams racing overhead will likely have poor seeing, and observers might choose to work on projects that are less sensitive to atmospheric turbulence. Temperature also plays a role, though in a more subtle way. Cold winter nights often have sharper, more dramatic twinkling than warm summer nights. This is partly because cold air is denser, and denser air creates stronger refraction. But it is also because winter weather patterns tend to feature sharper temperature contrasts. Cold polar air meeting warmer mid-latitude air, creating strong gradients and vigorous mixing. These temperature contrasts create what meteorologists call baroclinic zones, regions where air masses of different temperatures and densities meet and interact. The boundaries between these air masses are not smooth. They are turbulent, with eddies and waves forming along the interface as the different air masses slide past each other. Starlight passing through these zones gets bent and scattered by the turbulence, creating the dramatic twinkling characteristic of winter nights. The position of the jet stream also varies with season. In winter, the jet stream tends to be stronger and positioned farther south in the northern hemisphere, bringing its associated turbulence over more populated areas. In summer, it weakens and shifts north, often lying above the Arctic and leaving mid-latitude regions in relatively calmer air. This means that if you live at mid-latitudes, say in the United States, Europe, or Northern Asia, the jet stream is more likely to be overhead in winter than in summer. More jet stream activity means more shear, more turbulence, more dramatic twinkling. It is not a guarantee, of course. Weather is complex, and some winter nights can be remarkably stable. But the statistics favour more turbulent conditions in winter. Summer nights, particularly in stable summer weather, can have remarkably calm atmospheres. The temperature gradients are gentler, the air is less dense, and the mixing is often more subdued. Stars twinkle less, and when they do twinkle, the variations are smaller and smoother. This is why serious amateur astronomers in temperate climates often do their best planetary observing in summer, not because the planets are necessarily better positioned, but because the atmosphere is more likely to cooperate. There is a certain irony here. Winter skies are often clearer than summer skies, with fewer clouds and better transparency. But the very factors that create clear winter skies, strong high-pressure systems, cold, dense air, vigorous atmospheric circulation, also create turbulence that makes stars twinkle more. Summer skies can be hazier, but the stable, gentle conditions that create the haze can also create unusually good seeing. Local geography matters too. If you are near a large body of water, the water moderates local temperature, creating more stable air and often better seeing than locations inland. If you are in a valley, cold air can pool at night, creating temperature inversions, layers where cold air sits beneath warmer air, that can actually stabilize the atmosphere and reduce turbulence. Mountains create their own patterns. Air flowing over a mountain can create standing waves downwind, regions of organized up and down motion that persist for hours. These waves create regions of alternating stability and turbulence, and observing conditions can vary dramatically depending on whether you happen to be in a stable region or a turbulent one. All of this is to say that twinkling is not uniform, not even across a single night at a single location. It varies with altitude in the sky, with time as atmospheric conditions change, with local weather and geography, and the complex three-dimensional structure of air in motion. Experienced observers learn to use this variation. If they're planning to observe planets or the moon, objects where atmospheric steadiness matters because they want to see fine details, they watch the stars first. If stars are twinkling gently, conditions are likely good for planetary observation. If stars are twinkling dramatically, they might choose to observe other targets less affected by seeing, or to wait for conditions to improve. Some observers develop a feel for how twinkling changes through the night. Often, seeing improves after midnight. This is because the ground stops heating after sunset, and the temperature inversions that can trap turbulence near the surface begin to break down. The atmosphere settles, turbulence weakens. Stars that were twinkling dramatically at dusk might twinkle only gently by 2 or 3 in the morning. This is why many serious amateur astronomers do their best work in the early morning hours when others are asleep. It is not just about darker skies, though that helps too with fewer lights on and less atmospheric light pollution from distant cities. It is about the atmosphere itself becoming calmer, more stable, more cooperative as the night ages and the air settles into its nocturnal state. What appears to the casual observer as simple twinkling, stars that shimmer a bit, reveals itself on closer inspection to be a rich tapestry of effects, each one reflecting something specific about the atmosphere's state at that moment. Next time you're outside on a clear night, try this. Pick several stars at different heights in the sky. Watch them for a few minutes. Compare how they twinkle. The star overhead will likely twinkle gently, if at all. The star halfway up from the horizon will twinkle more noticeably. The star just above the horizon will twinkle dramatically, perhaps showing colours if it is bright enough. Watch how the twinkling changes over time, even over just a few minutes. You might see periods where all the stars steady briefly, then begin twinkling again as a new pocket of turbulence drifts through. You might see the twinkling speed up or slow down as the scale of atmospheric motion changes. You might see colours flash across a bright star near the horizon as particularly strong turbulence briefly separates the wavelengths. If you do this regularly, if you make a habit of watching how stars twinkle, you will begin to develop an intuition for atmospheric conditions. You will learn to distinguish between the gentle shimmer of a stable night and the frantic dance of a turbulent one. You will start to notice patterns, how seeing tends to improve after midnight, how certain weather patterns produce better or worse conditions, how the atmosphere has moods that change from hour to hour and night to night. This is not mystical. It is simply learning to read a language that has always been there, written in light from distant stars and decoded by your eyes every time you look up. The twinkling has information in it if you know how to look. You're watching the same atmosphere affecting different paths of light. The patterns you see, the differences in how these stars twinkle, are revealing the structure of the air above you, showing you how turbulence varies with altitude, how the atmosphere is layered and mixed and constantly changing. The twinkling is not just stars being affected by air. It is a language, a way the atmosphere communicates its structure and motion to anyone willing to watch and learn to read what they see. And the message translated says this: the air is never still, the temperature is never uniform, the turbulence is never simple. Every shimmer of starlight is evidence of complexity, of motion, of an atmosphere that refuses to be boring, even when it is completely transparent and invisible to our eyes. For all its beauty, atmospheric twinkling presents astronomers with a problem. The same turbulence that makes stars seem to dance also blurs and distorts the images that telescopes try to capture. Every time the atmosphere bends starlight, it moves the image slightly. Every fluctuation in brightness, every shimmer, every dance, all of it represents information being scrambled, details being lost, observations being degraded. A telescope, no matter how large or well made, cannot produce images sharper than the atmosphere allows. The theoretical limit of a telescope's resolution, the finest details it can distinguish, is determined by its aperture, by the width of its primary mirror or lens. A larger aperture means better resolution, the ability to see finer details. But this theoretical limit is almost never reached from the ground. The atmosphere interferes, turbulence blurs the image, spreads point sources into fuzzy blobs, makes fine details swim and waver. A large telescope, one that should in theory be able to resolve incredibly fine details, is limited instead by seeing by the atmospheric conditions at the moment of observation. On a night of poor seeing, even the largest telescopes on Earth perform no better than much smaller instruments. The aperture advantage is negated by atmospheric turbulence. The extra light-gathering power is still useful. You can see fainter objects, but the extra resolution is wasted because the atmosphere blurs everything anyway. This is why astronomers care so much about site selection. The best telescope in the world is only as good as the air above it. If you want to build a telescope that can capture sharp, detailed images, you need to put it somewhere with exceptionally stable atmosphere. Altitude helps. The higher you go, the less atmosphere sits above you, and less atmosphere means less turbulence. The best observatory sites are on high mountains, places like Mauna Kea in Hawaii, rising nearly 4,300 meters above sea level, or Cerro Paranal in Chile at 2,600 meters. At these altitudes, you are above a significant fraction of the atmosphere's mass, and more importantly, above much of the turbulent lower atmosphere where most of the trouble occurs. Dryness helps too. Water vapor in the air creates additional turbulence as it condenses and evaporates, and it also absorbs certain wavelengths of light that astronomers would prefer to observe. Dry sites, deserts, high plateaus, polar regions offer better seeing on average than humid sites at similar altitudes. Isolation from weather patterns helps as well. Some mountains create their own stable air conditions, sitting above the local weather in a region of exceptionally calm atmosphere. Mauna Kea is particularly good at this. The mountain creates stable air above its summit, air that is often calmer than at similar altitudes elsewhere. This is one reason why Mauna Kea hosts so many major telescopes, despite being in the middle of the Pacific Ocean, not exactly convenient for shipping large equipment. But even the best sites on Earth are not perfect. Even on Mauna Kea, on the best nights, there is still turbulence. Stars still twinkle, albeit gently. Images still blur, albeit less than they would at sea level. The atmosphere is thinner and calmer, but it is still there, still moving, still bending light in unpredictable ways. For a long time, this was simply accepted as a fundamental limitation of ground-based astronomy. You built your telescope on the best mountain you could find. You waited for nights of good seeing, and you accepted that your images would never be as sharp as theory suggested they could be. Then in the late 20th century, astronomers developed a solution: adaptive optics. The idea is conceptually elegant, if technically challenging. Instead of accepting atmospheric distortion, you measure it and correct for it in real time. An adaptive optics system includes several components working together. First, a wavefront sensor that measures how the atmosphere is currently distorting the incoming light. This sensor looks at a reference star, either a real star near the object you want to observe, or an artificial guide star created by shining a laser into the upper atmosphere and using the reflected light as a reference, and measures exactly how the atmospheric turbulence is bending that star's light. Second, a deformable mirror, a mirror whose surface can be rapidly changed by actuators pushing and pulling on its back surface. This mirror is controlled by a computer that takes the measurements from the wavefront sensor and calculates what shape the mirror needs to be to cancel out the atmospheric distortion. The system runs in a loop, measuring and correcting hundreds or thousands of times per second. The atmosphere distorts the light. The sensor measures the distortion. The computer calculates a correction. The deformable mirror changes shape to apply that correction. By the time the corrected light reaches the camera, the atmospheric distortion has been largely removed. It is, in essence, an incredibly sophisticated version of those eyeglasses that correct for the distortions in your eye's lens, except the distortions being corrected are changing hundreds of times per second, and the correction must be equally fast. When adaptive optics works well, the improvement is dramatic. Stars that were fuzzy blobs become sharp points. Planets that were smeared disks reveal fine surface details. Distant galaxies show structures that were completely invisible before. The telescope finally achieves something close to its theoretical resolution, limited by its aperture rather than by the atmosphere. This technology has transformed ground-based astronomy. Many of the sharpest images of planets, distant galaxies, and other celestial objects now come from ground-based telescopes equipped with adaptive optics, rivaling or even exceeding the quality of images from space telescopes in some cases. But adaptive optics is not magic. It has limitations. It works best for relatively bright objects, because you need enough light from the reference star to measure the atmospheric distortion accurately. It works over a limited field of view. The correction is only valid for a small patch of sky, because atmospheric turbulence varies across the sky, and a correction that works for one direction might not work for another direction even a short distance away. And it requires significant infrastructure and expertise. Adaptive optics systems are complex, expensive, and require skilled operators to maintain and adjust. Not every observatory has them, and even those that do only use them for observations where the improvement justifies the added complexity. The ultimate solution to atmospheric turbulence, of course, is to avoid the atmosphere entirely. This is why the Hubble Space Telescope was such a revolution when it launched in 1990. Hubble orbits above the atmosphere, in the vacuum of space, where there is no air to create turbulence, no seeing to limit resolution. From Hubble's vantage point, stars do not twinkle. They shine with perfectly steady light, their images sharp and stable. The telescope can observe for hours without atmospheric variations degrading the image. It can capture details that ground-based telescopes, even with adaptive optics, struggle to see. This is not to say that Hubble is better than ground-based telescopes in all ways. Hubble's mirror is relatively small, 2.4 meters in diameter, modest by the standards of modern ground-based observatories. The largest ground-based telescopes have mirrors 10 meters across or even larger, gathering far more light than Hubble can. When equipped with adaptive optics, these large telescopes can achieve resolution similar to Hubble's for bright objects, while collecting enough light to see much fainter things. But Hubble has the advantage of consistency. It does not depend on seeing conditions. It does not need adaptive optics. It simply works, night after night, or rather orbit after orbit, delivering sharp images without the complications of looking through an atmosphere. The James Webb Space Telescope, launched in late 2021, takes this even further. Webb orbits not around Earth, but at a gravitationally stable point far beyond the Moon, completely free from any residual atmospheric effects. Its larger mirror and infrared-optimized instruments allow it to see things Hubble cannot, all while enjoying the same freedom from atmospheric distortion. From Webb's perspective, the universe is perfectly sharp. Stars are mathematical points. Galaxies show structures down to the finest scales the telescope can resolve. There is no twinkling, no shimmer, no dance of light, just the steady, unwavering glow of objects as they truly are, unmediated by atmosphere. But atmospheric twinkling has taught us more than just that it is a nuisance to be overcome. It has also, somewhat ironically, become a tool for discovery. When a planet passes in front of a distant star, an event called a transit, the star's light dims very slightly as the planet blocks a tiny fraction of it. This dimming is small, typically less than 1%, even for large planets. Detecting it requires careful measurements of the star's brightness over time. Atmospheric turbulence makes these measurements harder because it causes the star's brightness to fluctuate randomly. The star twinkles, and that twinkling can mask the tiny, regular dimming caused by a transiting planet. But scientists have learned to work with this by making many repeated measurements and using statistical techniques to separate the random fluctuations of twinkling from the regular pattern of a planetary transit. They can detect planets around other stars, even from ground-based observatories. The twinkling becomes noise that can be filtered out, and the planetary signal emerges from beneath it. In some cases, atmospheric effects have even helped with planet detection. Scintillation, the technical term for twinkling, varies with the angular size of the source, as we have discussed. Stars twinkle, extended objects do not. If a star has a very close companion, close enough that the two appear as a single point to your eye but separable with precise measurements, the pattern of scintillation can be different from a truly single star. Astronomers have used this effect to detect binary stars and, in some cases, to constrain the properties of planetary systems. The way a star twinkles can tell you things about whether it is truly a point source or something slightly extended, information that can be useful when you are trying to understand what you are looking at. The study of twinkling has also improved our understanding of the atmosphere itself. By analysing how stars twinkle, how quickly the brightness changes, how the pattern varies with altitude and time of night, atmospheric scientists can infer things about turbulence in the upper atmosphere, about temperature gradients and wind patterns at altitudes that are difficult to measure directly. Weather balloons can sample the atmosphere up to about 30 kilometres. An aircraft can reach perhaps 20 kilometres. But above that, the atmosphere becomes difficult to probe directly. Satellites can look down from above, but they cannot easily measure what is happening within the atmospheric layers themselves. Stellar scintillation provides a way to probe these inaccessible layers. The twinkling pattern contains information about every layer of atmosphere the light passed through. By carefully analysing this pattern, ideally using multiple stars at different angles to sample different paths through the atmosphere, scientists can reconstruct something of the atmosphere's vertical structure, learning about turbulence and temperature at altitudes that are otherwise hard to study. There's a certain elegance to this. The same atmospheric turbulence that obscures our view of the universe can also, when properly understood and accounted for, provide information. Twinkling is not just a problem to solve. It is a phenomenon to study, to measure, to use as a tool for understanding both the atmosphere and the objects beyond it. This duality, twinkling as both obstacle and teacher, is common in science. The things that make observations difficult often turn out to contain information of their own. Noise is not just something to filter out. It can tell you about the properties of your instrument or your environment. Distortions are not just problems to correct. They can reveal the nature of whatever is causing the distortion. Twinkling teaches us to look more carefully, to measure more precisely, to think about what we are actually seeing rather than what we wish we were seeing. It forces astronomers to be clever, to develop better instruments and better techniques, to find ways to see through or around or in spite of the atmosphere. What began as a simple observation, stars twinkle, has led to an entire field of study. Atmospheric optics, seeing characterization, adaptive optics technology, scintillation measurements, all of it growing from the basic question of why starlight shimmers. It has also taught us humility. For all our technological sophistication, for all our ability to build telescopes that can see to the edge of the observable universe, we are still constrained by the thin shell of air that wraps around our planet. We can mitigate its effects with clever engineering, we can escape it entirely by going to space, but we cannot ignore it. Every image we capture from the ground, every observation we make of the cosmos, is filtered through our atmosphere. The twinkling reminds us of this. It is a constant visible demonstration that we are not passive observers of the universe. We are participants, embedded in our environment, seeing everything through the particular lens of our world's particular atmosphere. Other planets would show different twinkling patterns if they had astronomers looking up from their surfaces. Mars, with its thin atmosphere, would show minimal twinkling. Stars would shimmer less there than they do on Earth. Venus, with its thick, turbulent atmosphere, would show extreme twinkling, to the point where observing anything clearly would be nearly impossible even if you could somehow survive the surface conditions. A hypothetical observer on Titan, Saturn's largest moon, would see stars twinkle through Titan's thick nitrogen atmosphere. But the twinkling would be different, slower perhaps, because Titan's atmosphere is so cold that turbulence might develop on different scales than it does on Earth. We cannot know for certain without measurements, but we know it would be different, because every atmosphere is unique. The twinkling we see from Earth is thus specific to Earth. It is part of our world's signature, part of what makes observing from our particular vantage point different from observing from anywhere else. When we look up and see stars shimmer, we are not just seeing the stars. We are seeing our atmosphere's response to starlight, seeing our world's unique way of interacting with light from the cosmos. And perhaps that is fitting. We belong to this planet, to this atmosphere. The air that makes stars twinkle is the same air that allows us to breathe, to live, to exist at all. The turbulence that frustrates astronomers is driven by the same solar heating that makes our world habitable. The twinkling, then, is not separate from us. It is part of what it means to observe the universe from Earth, from inside our ocean of air, from the only vantage point we have ever known. We have followed a photon across the cosmos. We have learned about refraction and turbulence, about why planets shine steady while stars dance, about the patterns that reveal themselves in twinkling light. We have seen how astronomers fight against atmospheric distortion and how they have learned to use it as a tool. But there is something else here, something that goes beyond the physics and the astronomy. There is beauty in the simple act of watching stars twinkle, a kind of beauty that deepens when you understand what you are seeing. When you look up at a twinkling star, you are witnessing something quietly miraculous. Light that left a distant sun years or decades or centuries ago, light that has crossed distances so vast that the human mind struggles to hold them, light that has travelled through the perfect emptiness of space, maintaining its direction and energy. That light trembles in its final passage through our ocean of air. The twinkling makes visible what is usually invisible. You cannot see the atmosphere directly. It is transparent, ever-present, but imperceptible. You move through it without noticing, breathe it without thinking, but starlight reveals it. Every shimmer is the air making itself known, announcing its presence in the only language available, the bending of light. Think about what this means for a moment. The air above you is moving right now. Wind you cannot feel is carrying pockets of warm and cool air across the sky, mixing them, creating eddies and currents at altitudes measured in kilometers. This motion is constant, has been constant for as long as Earth has had an atmosphere, will continue for as long as the planet remains warm enough to drive convection. And every clear night this invisible motion writes itself across the sky in the dance of starlight. The atmosphere speaks in flickers and shimmers, in the gentle pulsing of distant suns, in colours that flash across bright stars near the horizon. The message is simple. I am here. I am moving. I am alive with energy and motion. There is something profound about the way the universe conspires to make this visible. Stars had to exist, burning steadily for billions of years. Space had to be empty enough that their light could cross it unchanged. Earth had to develop an atmosphere thick enough to create turbulence, but transparent enough to let starlight through. And you had to be there, looking up, with eyes capable of detecting these tiny variations in brightness. All these pieces had to come together: stellar evolution, the vacuum of space, atmospheric physics, biology, consciousness itself, just so you could lie on grass on a summer night and watch stars shimmer. The twinkling is not for us, of course. The stars do not know we exist. The atmosphere does not perform for an audience, but we can appreciate it anyway, can find meaning in it, can let it tell us things about the nature of light and air, and the distances between stars. Every culture that has watched the night sky has noticed twinkling, and many have woven it into their stories and songs. Stars that twinkle have been called dancing stars, living stars, breathing stars. They have been seen as signals, as omens, as the eyes of ancestors or gods watching from the heavens. The shimmer made stars seem animate, responsive, present in a way that steady light could not. Ancient navigators learned to trust steady lights over twinkling ones when identifying guide stars. Without knowing the physics, they understood that twinkling meant uncertainty, that a star's apparent position could shift, that its brightness could fluctuate, that it was somehow less reliable as a fixed point of reference. The planets, shining steadily, became particularly important for navigation precisely because their calm light could be counted on. Poets wrote about twinkling as evidence of life in the heavens, as stars communicating across the void. And in a metaphorical sense, they were right. The twinkling is communication, just not from the stars. It is the atmosphere communicating its state, its motion, its constant restless energy. We know now that the animation is not in the stars but in our atmosphere, that the responsiveness is the air responding to solar heating and the rotation of the planet. The magic, if we want to call it that, is not supernatural. It is physics, explicable and measurable. But knowing the mechanism does not diminish the experience. If anything, it enriches it. Now, when you watch a star twinkle, you can understand the whole chain of causation. Sunlight heating the ground unevenly, warm air rising, turbulence forming, starlight bending through the churning atmosphere, your eye detecting the variations. You're watching physics in action, watching the universe demonstrate its laws in real time. There is a common worry that understanding something scientifically somehow strips away its beauty, that explaining the rainbow reduces it to mere refraction, that analysing a sunset turns it into wavelength scattering. But this has never been true. Beauty survives explanation. Wonder survives understanding. The person who understands why stars twinkle is not diminished in their appreciation. They are enhanced. They can look up and see not just pretty lights, but a demonstration of fluid dynamics, a revelation of atmospheric structure, a visible signature of processes operating on scales from millimeters to kilometers. The twinkling becomes layered with meaning, each layer adding depth rather than replacing what came before. The poet who wrote about stars twinkling like diamonds was responding to something real, something beautiful. The astronomer who built adaptive optics to correct for that twinkling was responding to the same phenomenon, just with different tools and different goals. Both are valid responses to the same natural wonder. There's room for both poetry and physics here, room to be moved by the beauty of twinkling starlight and to understand the atmospheric turbulence that creates it, room to appreciate the dance and to measure it, to feel wonder and to explain it. The atmosphere, this ocean of air we live in, mediates everything we see. Every photon from every star must pass through it before reaching our eyes. And in passing through, the light is changed, not in its essential nature, but in its path, its apparent position, its moment-to-moment brightness. This mediation is inescapable from the ground. We cannot see the universe directly. We see it through our atmosphere, and our atmosphere leaves its signature on everything we observe. The twinkling is part of that signature, part of what it means to view the cosmos from Earth rather than from empty space. But the atmosphere does more than distort. It also protects. The same air that makes stars twinkle also shields us from harmful radiation, burns up meteors before they can reach the surface, holds the warmth that makes liquid water possible. The turbulence that frustrates astronomers is driven by the same processes that distribute heat around the planet, that create weather, that make Earth habitable. We complain about the atmosphere when it interferes with our observations, but we depend on it for everything. Every breath you take, every moment you remain alive is possible because of this envelope of gas held close by Earth's gravity. The twinkling is a small price to pay for being able to exist in the first place. When you watch stars twinkle, you are seeing the atmosphere that sustains you. You are watching it move, watching it respond to heat and gravity and the rotation of the planet beneath it. The dance is not separate from you. You are part of the same system, breathing the same air, warmed by the same sun that heats the ground and drives the turbulence overhead. There's an intimacy to this that we rarely acknowledge. The air is not out there, separate from us. We are inside it, immersed in it, constituted partly by it. The oxygen in your bloodstream came from this atmosphere. The carbon in your bones cycled through it. The nitrogen in your proteins was mixed and distributed by the same atmospheric circulation that makes stars dance. The twinkling connects you to the atmosphere in a direct, visible way. It says, here is air in motion. Here is turbulence you cannot feel, but that light can detect. Here is evidence of the same processes that keep you alive, revealed in the shimmer of ancient starlight. Perhaps this is why twinkling stars have always captured human attention. Not just because they are pretty, though they are. Not just because they seem alive, though they do. But because, on some level, even before we understood the physics, we recognized that the twinkling was telling us something about our world, about the air we move through, about the envelope that separates us from the void. The stars themselves are remote, unreachable, belonging to distances we can barely conceive. But the twinkling belongs to us. It happens here, in our atmosphere, in the space between the stars and our eyes. It is local, immediate, ours in a way that the stars can never be. When children sing about twinkling stars, they are singing about something they have noticed, something real. The words might be simple: twinkle, twinkle, little star, how I wonder what you are, but the observation is accurate. Stars do twinkle. They do seem to wonder, to question, to pulse with something that looks like life. And now you know what they are. Not the stars themselves, distant suns, fusion reactors burning in the void, but the twinkling. The twinkling is air in motion, temperature differences made visible, the atmosphere speaking in light. Understanding this does not make the twinkling less wonderful. If anything, it makes it more so. The simplicity of the observation, stars shimmer, leads to an understanding of atmospheric physics, of refraction and turbulence, of convection and temperature gradients. Simple beauty opens onto complex truth, and the complex truth somehow circles back to beauty again. Next time you're outside on a clear night, take a moment to really watch the stars twinkle. Not just glancing up, but actually watching, paying attention to how the light changes, how different stars behave differently, how the shimmer varies with position in the sky. You are watching something ancient, light from stars that may have died before their light reached you. You are watching something immediate, turbulence happening right now, right overhead. You are watching your atmosphere reveal itself, using starlight as a tool, showing you motion that would otherwise be invisible. The poetry and the physics are both there, both true, both worth appreciating. The stars twinkle because the air cannot hold still, and in that restless motion, in that constant churning of warm and cool, in that invisible dance made visible by light from distant suns, there is something beautiful, something worth watching, something worth understanding, something worth lying on grass to see, on a clear night when the stars come out and begin their gentle dance above you. We have followed a photon across the cosmos. We have learned about refraction and turbulence, about why planets shine steady while stars shimmer. We have discovered that the twinkling is not in the stars at all, but in the last 100 miles of the journey, in our ocean of air making itself visible. And now we come back, back to the present, back to the clear night sky above you, wherever you are. The stars have not changed. They are still burning steadily, as they have been for millions or billions of years, still sending their light across the void in perfectly straight lines, still indifferent to the gentle dance our atmosphere creates in their final moments before reaching your eyes. The atmosphere has not changed either, still churning with invisible currents, still mixing warm and cool air in patterns that shift from moment to moment, still bending starlight, still making the distant suns shimmer, still speaking in a language of light that you now understand. If you have enjoyed this journey through twinkling light tonight, if understanding the dance has made the stars more beautiful rather than less, don't forget to follow the sleepy astronomer. There are more cosmic wonders to explore together, more quiet mysteries hiding in plain sight, more opportunities to understand what we see when we look up. And if this particular mystery resonated with you, a like helps others discover these peaceful explorations of the universe above us. Thank you for watching the stars dance with me, for learning to read the shimmer, to see the atmosphere in motion, to understand that the twinkling is our world making itself known. This is the sleepy astronomer, wishing you clear skies, peaceful dreams, and the gentle comfort of knowing why the stars seem to breathe. Good night, and sleep well beneath dancing starlight.